Hi, my name is Isabella St. Pierre-Charles, and today we're going to discuss imperfections in solids, a topic in material science and its application to catalysis. So when it comes to imperfections in solids, we can look at it as in 3 dimensions. 1 dimension, point defects, 2 dimension, linear defects, and 3-dimensional volume defects. There are 3 kinds of point defects. The first kind are interstitial defects, which is the insertion of an extra atom. Now this atom can be the same as the original substance, or it can be a different atom, an impurity. There are also vacancies when the original atom is not present, or substitutional, where there is a different atom in place of the original one in the structure. For linear defects, these are of course occurring along a line. For an edge dislocation, there is an extra half plane of atoms that creates a discrepancy in the original structure. A screw dislocation is formed by shear stress and shifts the original structure in a slightly different direction. Bulk or volume defects can be visible via pores or cracks. These are larger defects formed by accumulations of the previously mentioned defects, specifically edge and screw dislocations. Imperfections are present in catalysts. The surface imperfections in catalysts or the bulk volume defects in catalysts allow reactions to take place. A surface defect in a catalyst could be some sort of different atom that reacts on the surface to form a new substance. A volume defect could allow the substance to disperse into the catalyst and allow the reaction and or chain growth mechanism to take place inside of the pores. One example of this would be an iron cesium catalyst on the surface of silicon oxide for FTS. In this process, on the surface of SiO2, cesium helps oxide form the oxide phase, which helps convert carbon dioxide to carbon monoxide. Then with the feed, cesium also helps iron form the carbide phase. This carbide phase takes the previously formed carbon monoxide, reacts with feed hydrogen to form long-chain hydrocarbons on the surface of the SiO2. In this example, the SiO2 provides support for the surface, allowing the long-chain hydrocarbons to form on its surface. Now we will see examples of all of these kinds of imperfections. Here we will reference the PowerPoint for review of the names. As an interstitial example, we have a self-interstitial atom over here. Now, this, as you can see, we have 3 and 3, 3 and 3, and then there's an extra column in this row of atoms. This would be an example of a line defect that is called an edge dislocation. So as you can see, the extra half plane of atoms is on this top row, and the extra half plane is this column, which causes the edge dislocation between these two. The screw dislocation is formed by shear stress, and as you can see, if shear stress was applied along this surface, now there is a new direction of the plane. A couple more examples are impurities. So here's an example of a different kind of atoms from the original. So for example, if this is SiO2, this could be cesium, and it's an impurity within, as opposed to this interstitial, which is a self-interstitial. So this would also be silicon oxide. Additionally, we have a substitution. So here, although it's not interstitial, it's not disrupting the formation, in this case BCC, but it is a different atom than the original. And then up here, we can see an example of how this would be applied to catalysis. So we can imagine that on here, on top, this blue represents silicon oxide, the green represents iron, and the red represents cesium, and the carbon dioxide and hydrogen would be fed, they would come on the surface, and they would react with the iron oxide and carbide states formed on the surface of the SiO2. And with respect to the SiO2, the iron would either be a substitution, or it could be an impurity, and then the cesium would also be an impurity.